You walk into your garden to find bright yellow blossoms popping up all over the vines, the universal sign of a massive summer harvest. But a few days later, those flowers are snapping off at the stem. They drop into the dirt, leaving empty vines where fruit should be. When this happens, the instinct is to assume the plant is dying, which leads to panicked remedies like flooding the roots with extra water or dumping heavy fertilizer into the soil. Instead of failing, the plant is actually executing a highly calculated survival protocol. Solving the mystery of the vanishing tomatoes requires treating the plant as a ruthless biological energy manager, constantly calculating its return on investment. To see how that calculation works, we have to look inside a single blossom. Growing a water-heavy fruit requires a massive expenditure of energy, so the plant requires perfect conditions before it commits to the process. Tomatoes are self-pollinating. Every individual flower comes equipped with both male and female reproductive parts, meaning the pollen only has to travel a microscopic distance within the blossom to trigger fruit production. Yet possessing the biological tools is only the first step. The plant monitors its surrounding environment, checking the math on a strict set of variables before it allows fertilization to proceed. This scale shows the first major constraint, temperature. If daytime heat rises above 32 degrees Celsius, or if nighttime lows drop below 13 degrees, the pollen becomes sterile. The flower looks fine on the outside, but the internal mechanism has shut down. The same strict rules apply to humidity. High humidity causes pollen grains to clump together, while extremely dry air turns the pollen into useless dust before it can reach its target. Finally, there is the kinetic requirement. Because the pollen is housed internally, the flower relies on physical vibration, like the wind or a buzzing bee, to shake the particles loose so they can fall into place. If any single variable, temperature, humidity, or physical vibration, fails to align perfectly, the internal machinery stalls, and fertilization becomes mathematically impossible. But the math extends beyond the individual flower to the entire organism. Tomato plants are heavy feeders and drinkers, requiring massive resources from the soil to maintain their baseline health. Sudden stressors like inconsistent watering, disturbed roots, or nutrient imbalances immediately register as threats to the plant's core system. This split screen shows how excessive nitrogen fertilizer disrupts that system. On the right, the plant has dumped all its energy into growing massive leaves. The foliage looks impressive, but it consumes so much energy that the plant produces zero flowers. When these macro stressors hit, the plant engages a biological failsafe, shifting out of reproductive mode and into survival mode. To conserve its dwindling energy, the plant initiates an abort sequence. It deliberately severs the cellular connection between the main stem and the blossom. Dropping that blossom is an act of biological triage. The plant sacrifices the offspring to ensure the main organism survives the period of stress. A fallen yellow flower on the soil is a direct, vital signal from the plant. This feedback allows you to act as a partner in the plant's energy management. You can directly adjust the microclimate causing the stress instead of relying on guesswork. If your tomatoes are sheltered indoors or in a greenhouse, you can solve the kinetic problem by manually tapping the stems or gently shaking the flower clusters to simulate the wind and trigger trellination. During severe heat waves, deploying a shade cloth over the garden can cool the ambient air. In an unexpected cold snap, you can protect the plant's energy by holding off on heavy watering until temperatures stabilize. This triage protocol is only a temporary defensive measure, and tomato plants are remarkably resilient. The moment conditions stabilize and the energy math balances, the plant exits survival mode. It reinitiates the reproductive sequence, pushing nutrients directly into fruit production. That next wave of blossoms proves the tomato plant was never failing. It was simply protecting its resources, waiting for the perfect mathematical moment to build the harvest.